This is Porterville College, Physics 104A, Chapter 3 Homework Solutions. Starting with number 19, an object is moving at 18 meters per second at 220 degrees counterclockwise from the x-axis. Find the x and y components of its velocity. So, it's good to draw a picture to see what it's talking about. Now, 220 degrees counterclockwise from the x-axis, that is how we normally define our angles. So, in this case, theta is 220 degrees, and there it is. We have in the pink the v vector. We want to find the x and y components. So the x component of any vector is v times cosine of its angle, or magnitude times the cosine of the angle. The y component is the magnitude times sine of the angle. So when we do for the x component, 18 meters per second times cosine of 220 degrees, we get negative 14 meters per second. For the y component, when we do 18 meters per second times the sine of 220 degrees, we get negative 12 meters per second. And those answers that we get, we see that it's confirmed by the picture that we've drawn. We expect it to be negative in both directions. And so to write this in vector notation, we can say that the v vector is negative 14i hat minus 12j hat meters per second. For number 21, an object's velocity is given. What's the direction of the object's acceleration? So, acceleration vector is the time derivative of the velocity vector. So in the I hat direction, the derivative of ct cubed is 3t squared. So we have 3t squared I hat. In the y direction, this becomes 0. So we don't even bother to write plus 0 j hat. We just leave that out. So the acceleration vector is 3ct squared I hat. Now the question is asking, what is the direction of the acceleration? The magnitude is 3ct squared, but the direction, since it's all in the I hat direction, that's going to be along the x-axis. So we could say theta equals 0 degrees. For number 25, an object is moving in the x direction. It undergoes an acceleration in the y direction. Find its velocity vector. So initial velocity is 1.3 I hat. Acceleration is 0.52 j hat. That's in the y direction for a time of 4.4 seconds. So for the final velocity, we use final velocity vector equals initial velocity plus acceleration times time. Here I've written it in the stacked unit notation. So what this means, these brackets here, mean the 1.3 is in the x direction, the 0 is in the y direction. So that's just another way of writing 1.3 I hat plus 0 j hat. So that's v naught plus time of 4.4 seconds times the acceleration, 0 I hat plus 0.52 j hat. So the stacked notation is just the x component and the y component, meters per second squared. When we add those together, the top row of my brackets is the x component, the bottom row is the y component. So what this whole thing here is just the 1.3 plus 4.4 times 0. That's the x component. The bottom row is the y component, 0 plus 4.4 times 0.52. And I've written it like that. So 1.3 plus 0 times 4.4 in the x direction gives us 1.3. In the y direction, 0 plus 4.4 times 0.52, that gives us 2.3 in the y direction. So here's our vector. Now for the final answer, down below where I have my red pen, I've rewritten this in unit vector notation. So I've written it as 1.3 I hat plus 2.3 j hat meters per second. Next is number 30. Position of the object is given. Find the object's acceleration. And here I've written it in the stacked vector notation. Here's the I hat, or the x component. The second row is the y component, or the j hat. Acceleration is the second derivative of this. So in this line, I've written the velocity vector, which is the first derivative. Then acceleration is the derivative of that, which gives us 3.6 in the x component and negative 4.8 in the y component, meters per second squared. So I'll rewrite this in terms of unit vector notation. So I'll say 3.6 I hat minus 4.8 j hat, meters per second squared. Number 32. Tossing an apple horizontally, simultaneously drop a peach from the same height. How long does it take each to reach the ground? It's good to draw a picture. So we have the apple going initially in the x direction, 8.7 meters per second. The peach just gets dropped from rest. Set up your coordinate system. I've made y, the positive y-axis, go downward, because all motion is downward. You should recognize it's the same time for both. Regardless of the apple's horizontal velocity, it's still going to fall at the same rate, because all things accelerate towards the Earth in a vertical acceleration of 9.8 meters per second squared. So it's going to be the same time for both. We can use this equation, y equals y naught plus v naught yt plus 1/2 ayt squared. We're going to need the, well, initial velocity in the y direction. You can realize that for both of them it's 0. Even though the apple was moving in the x direction, its initial y direction velocity is 0. Same with the peach. However, I've expanded it here just so you can see the trig will always give you the answer if you can't come up with it through that reasoning. V naught y is v naught sine theta. So for the apple, v naught sine theta, v naught is 8.7 meters per second. It's moving at an angle of 0 degrees, so times sine of 0 degrees becomes 0 meters per second. For the peach, you don't have to worry about its angle that it was moving. It wasn't moving at all, so v naught is 0. Therefore, certainly its v naught sine theta is going to be 0. And what these two lines just go to show, if you couldn't reason it out from just thinking about the motion, initially both the apple and the peach had 0 vertical velocity. So now let's go back to this equation right here with y equals. The v naught yt goes away because it's 0, and we're left with 1/2 times acceleration times t squared. And remember, acceleration in the y direction is g. So we're left with this equation here. Y equals 1/2 gt squared. We know what y is. They both fall 2.6 meters. We want to solve for t. So solving this for t gives us t equals the square root of 2y over g. Y is 2.6 meters. G is 9.8 meters per second squared. And so we get 0.73 seconds. That's how much time it takes for both of them to hit the ground. Number 33, look at the picture that I've drawn and the equation, and I'll comment on it in a minute. You notice with the picture, I've drawn the y-axis, positive y direction, go down. And that's a choice that you can make. I like to do that when the motion is going to be downward, but not essential. You can make your axes go whichever way you want them, whichever way you think will be most convenient. It's tossed horizontally, so theta naught is going to be 0 degrees. Off an 8.8 meter high roof at 11 meters per second. How much time to reach the ground? How far does it move horizontally? So the time question, this is going to be just like the previous problem with the apples and the peach. We can say y equals y naught, and I'm starting y naught at 0, plus v naught yt, just like with the apple and the peach, all its motion was horizontal. It wasn't at any angle other than 0 degrees, so that term's going to go to 0. And we're left with y equals 1/2 acceleration in the y direction times t squared. Acceleration in the y direction is g, so we have y equals 1/2 gt squared. Just as with the previous problem with the apples and the peach, we solve this for t. T equals the square root of 2y over g, and we get 1.34 seconds. Question B asks, how far does it move horizontally? Well, now that we know the time, the distance equals initial x velocity times t. We don't have to worry about acceleration, because with projectile motion there is no acceleration in the x direction. So it was originally moving horizontally at 11 meters per second. It will continue moving horizontally at 11 meters per second till it hits something. So 11 meters per second times the time of 1.34 seconds, it will go 15 meters far before it hits the ground. Number 34. And once again, this is an object that's fired horizontally. This time an arrow, 41 meters per second, travels 23 meters horizontally. From what height was it fired? Notice the setup that I've done. I've drawn my coordinate system, y going down, x to the right. I started at x naught equals 0, y naught equals 0. X equals 23, and now I'm looking for y is the information we're trying to figure out. How far does it go downward before it, when it hits the ground? So we know the distance it's going to travel, 23 meters. We know its velocity. We can solve for its time. Time is going to be the distance it's going to travel divided by its horizontal velocity. So 23 meters divided by 41 meters per second. And we get a time of 0.56 seconds. Now that we know how much time it's in the air, we can figure out how far it can fall using this equation. This kinematic equation, y equals y naught goes to 0, plus v naught yt, that goes to 0. And all we're left with is 1/2 gt squared. So y equals 1/2 times 9.8 times the time squared. And we get that the arrow falls 1.5 meters. Number 38, very basic, straightforward problem involving uniform circular motion. Radius of 75 meters. We want acceleration to be numerically equal to that of gravity, which means 9.8 meters per second squared. So we have a equals v squared over r. Let a equals g, so g equals v squared over r. And then we're going to solve for v. V equals then the square root of rg. Plug in those numbers. Radius is 75 meters. G is 9.8 meters per second squared, and we get 27 meters per second. Estimate the acceleration of the moon, which completes a nearly circular orbit of 385,000 kilometers radius in 27 days. Okay, we want to solve for the acceleration, so we know we're going to need a equals v squared over r. But the problem isn't giving us the speed of the moon. So here's what we need for v. Think of one orbit of the moon. It goes around the circumference of its orbit, which is 2 pi r, and it does it in a time t. That's going to be 27 days. So the distance it goes, one time around, divided by the time, and that'll be its speed. So when we plug in this value for v equals 2 pi r over t, plug it into this a equation, then we have a equals 2 pi r over t squared. That's what v squared was. And we still have this divided by r. You can simplify it a bit and end up with 4 pi squared r over t squared. Input all the numbers, so you're going to need for the radius, the book says 385,000 kilometers, but we need this in MKS units, meaning meters. So 385,000 kilometers is going to be 385 million meters. You need to figure out how many seconds 27 days is. So 27 days times 24 hours times 3,600, and you get about 2.3 million seconds. Square that. And we get an acceleration, very small acceleration, 2.8 millimeters per second squared. Number 44. Biology problem here. Biologist is looking through a microscope, sees a bacterium at that position. After 6.2 seconds, it's at the next position. Find its average velocity and its average speed. Okay, velocity vector, average velocity vector is displacement vector over time. Remember that displacement is r2 minus r1. I've written this in my stacked notation. So 4.6 I hat plus 0 j hat plus 1.9 k hat. That's what this means. This is r2 vector minus r1 vector. The units are micrometers, and we're going to divide by 6.2 seconds. When I subtract these, 4.6 minus 2.2 gives 2.4. 0 minus 3.7 in the y direction gives negative 3.7. And in the z direction, 1.9 minus negative 1.2 gives 3.1. So what I've got here in the numerator is the displacement vector, micrometers, still dividing by 6.2 seconds. So when I divide each of these by 6.2 seconds, I get this answer. And I've written it in the unit vector notation. Average velocity vector is 0.39 I hat minus 0.60 j hat plus 0.50 k hat, micrometers per second. The next part of the question asks what is its average speed, and speed is just magnitude of velocity. So you're going to use Pythagorean theorem three-dimensionally. Your x squared plus your y squared plus your z squared, square root it, and you should get an average speed of 0.87, whoops, bad units, how's that? Micrometers per second. Number 54. We have displacement, or the initial position, that's at the origin, so 0, 0. Initial velocity and acceleration. Question A asks, when does the particle cross the x-axis? So mathematically, another way of asking that is, as I've written, when is x equal to 0? We know that x is equal to 0 at time equals 0, so we expect that as a solution, but we're going to ignore that. We're looking for the non-zero time when x is equal to 0. So we can use this equation, x equals x naught plus v naught xt plus 1/2 axt squared. Plug in the values that we know. We're looking for when x equals 0, so plug it in. X naught is 0 because that's the given information. velocity initially in the x direction is 11 times t. Acceleration, we're doing plus 1/2 of the acceleration in the x direction. Acceleration in the x direction was negative 1.2. Half of that then is going to be minus 0.6 t squared. So when we solve this, we can factor out t and get 0 equals t times 11 minus 0.6 t. So t equals 0 is one solution. We already, that's not what we're looking for. That just says that it was at the x-axis when it started. We already knew that. This is what's important. The other solution, 11 minus 0.6 t equals 0. So we get t equals 18.3 seconds. Question B asks, what is its y-coordinate at the time? Meaning when it crosses the axis. So use this equation. Y equals initial y, which is 0, plus v naught yt, 14 times 18.333 seconds, plus 1/2 times acceleration in the y direction, which was 0.26, times the time squared, and we get 300 meters. Question C, how fast is it moving and in what direction? And implied in that is at the time 18.3 seconds. So how fast is it moving? Let's use our velocity equation. Velocity is v naught plus at. I've plugged in those numbers, so initial velocity is 11 and 14 in the x and y direction, plus here's your acceleration. You're going to distribute the 18.3 onto each of these, meaning negative 1.2 times 18.3 and 0.26 times 18.3. So to get the x direction, the answer you can see is negative 11, but just do the x values. So 11 plus negative 1.2 times 18.3, and that gives negative 11. To get the y direction, you do 14 plus 0.26 times 18.33, and that gives 18.76. So this is the velocity vector, negative 11 I hat plus 18.76 j hat. And I've drawn a little picture of it there showing approximately where it's going. And then I want to know what is its speed and what is its angle. So I use Pythagorean theorem between negative 11 and 18.76, and I get a speed of 22 meters per second. To find the angle, I take the arctan of Vy over Vx. That gives me negative 60 degrees, and I realize negative 60 is a fourth quadrant answer. I'm interested in the second quadrant, and I realize to adjust I have to add 180 degrees. So I get a direction of 120 degrees. Last problem, some fun calculus here. Number 75 gives the range equation. It's a combination of putting x's and y's together, and it specifically deals with the range, the distance horizontally that a projectile will go when it comes down to its original height that it started at. And it's this, x equals v naught squared over g times sine 2 theta. And the question says, using calculus, we're going to take the derivative, the derivative, and set it equal to 0 to find that the maximum range is 45 degrees. And by the way, setting equal to 0 also finds the minimum, so we're going to find both the maximum and the minimum range. So we're taking the derivative. In this case, we're doing the derivative with respect to theta. So dx over dx d theta, v naught squared g is a constant, so you throw that off to the side, and then you're doing d theta of sine 2 theta. You still have your v naught squared over g off to the side. When we take the derivative of sine 2 theta, we get cosine 2 theta times the derivative of the argument, 2 theta. So here's our v naught squared g that we threw off to the side, times cosine 2 theta, and the derivative of 2 theta is 2. And we've set the derivative equal to 0. That's how you find a maximum and minimum. So what values of theta is this going to be 0? You can ignore the v naught squared over g and 2. Those aren't going to be equal to 0. And we're left with cosine 2 theta equals 0. Okay? So for a cosine to be equal to 0, that angle has to be either up here at 90 degrees or down here at 270. But that doesn't mean the angle is 90 or 270. That means the cosine of whatever you're taking, the cosine of the argument. So in this case, that argument is 2 theta. So 2 theta is either 90 degrees or 270 degrees. Those are our solutions. Theta equals, when we say it's 90 degrees, 2 theta is 90 degrees, then theta is 45 degrees. And that shows that we get the maximum range at 45 degrees. By the way, the other solution, where 2 theta is 270, that gives theta of 135. That's for the minimum range. What that actually is, that is getting a maximum range in the wrong direction. If you think which way 135 degrees is, if you want to imagine we have a cannon here firing to the right, we want to get the maximum range to the right. The worst possible direction to throw something is at 135 degrees. You will get maximum range, but in entirely the wrong direction.